back to geometry. We're in section 5.4. We're mid-chapter, finishing up this kind of first grouping, 5.1 to 5.4. There's a lot jam-packed in here. Now we're going to talk about something called the mid-segment of a triangle. And this is really cool. It's basically a segment that joins or connects midpoints of two sides of the triangle. So every triangle has three mid-segments, and that forms, in and of itself, a smaller triangle inside the bigger one. That's really cool. So as you look at this figure, X is the midpoint of PQ, and Y is the midpoint of QR. And when you connect X and Y, that's what we call, that's a mid-segment, okay? And it should be parallel to, XY should be parallel to PR, okay? And then let's look at Z. Z is the midpoint of PR. If you connect XZ together, that's actually a mid-segment, and that should be XZ should be parallel to QR. And YZ is a mid-segment, and YZ should be parallel to PQ. So we've got a triangle within a triangle, and that happens when you connect all the midpoints together, forming three separate segments, and in and of themselves, they form their own triangle. Okay, so hopefully that makes sense so far. Let me show you example one. I'm sorry it's so much smaller, but this was just such good stuff. I wanted to make sure you saw every bit of it, and I wanted to give you a little bonus to try on your own. So we're going to examine mid-segments in the coordinate plane, and we've got triangle GHJ. Shows that the mid-segment KL is parallel. We need to show mid-segment KL is parallel to GJ. We want to prove that mathematically. And then we want to prove that KL is actually half the distance of GJ. So the first thing we want to do, first thing I want to calculate are the coordinates of KL. I want to figure out what those 2 points are. I'm going to need to know the name of those 2 points. I know you can tell from the graph, but you may not have the graph. Like in the check it out, they didn't leave you a graph. You have to do everything by yourself. So we'll have to figure all that out on our own. So KL, let's look at K first of all. K is the midpoint of HG. So if you look at HG, let's write that down, midpoint HG. We want to add the -5, which is the X of the point H, and the G, the X there is -7. We want to add those X's together. -5 and -7, -12. Divided by 2 is -6, okay? And then do the same thing with the y's. 6 plus -2 is 4. 4 divided by 2 is 2. So this is point K right here, -6, 2. Now we want to find the midpoint of HJ. Okay, do the same thing. We're going to do the midpoint formula. Add your x's divided by 2. Add your y's divided by 2. So -5 plus 1 is -4. And -4 divided by 2 is -2. And then we're going to do the same thing with the y's. 6 plus 2 is 8. 8 divided by 2 is 4. So there's your L right there. There's K, the coordinates for point K and the coordinates for point L. Should be at -6, 2 for K, and if you count it out, it'll work out. Here's 1, 2, 3, 4. Here's -6, +2. So it is at -6, +2, and then -2, 1, 2, 3, 4 is L. So it works. I can clearly see that on the graph that that's how it worked out. Okay, you may not have a graph. So you may, like in your check it out, there is no graph. You have to create the graph and figure it out on your own. So I do want to show you and remind you how to use the midpoint formula to find those midpoints on each of your segments there. Okay, so we want to compare the slopes. Once you've got it drawn out on graph paper, then it's really simple to use rise over run. And I actually prefer rise over run. If it's already graphed, rise over run. If it's not, use the slope formula. So KL, the slope of KL, you start here, put your pencil tip on K. We're going to go up 2. Now we're on the same level as L. So KL, we went up 2. And now we're going to go right 1, 2, 3, 4. Up to right 4. Well, that slope is 1/2. So that's the slope of KL. GJ, let's look at GJ. So I'm going to start here at G. And I'm going to go up 1, 2, 3, 4. Now I'm on the same level as J. So I went up 4. Okay, that's great. And now I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8. Well, 4/8 reduces to 1/2. Okay, so we're comparing the slopes of KL and GJ, and we can conclusively determine that segment KL is actually parallel to GJ because they have the same point that are the same slope. And that's what we know about parallel lines. Parallel lines have the same slope. So that is what you're looking for, same slope. If they do not have the same slope, then they are not parallel. So that is something, that's what I want to verify. I like using rise over run. You could also use the points and plug into the slope formula. So I'll give you 2 options, rise over run. I like to use that on graphs, or slope formula. If I know the names of the 2 points, then I can just plug them in and calculate it myself. Whatever you're comfortable with, I'm comfortable with, okay? Now we've got to compare the lengths of KL and GJ. So that, again, we've got to go back to a formula that we use occasionally called the distance formula. You're going to subtract your x's, square that difference. Subtract your y's, square that difference. Add those 2 square differences together, take the square root, and you're going to have the distance of that particular segment. That's why we need to know the names of the points so I can actually calculate those distances. All right, so to find KL, I had to know that K is -6 and L is -2. So let's start with KL, finding that distance. So I'm going to do the square root of, first thing I want to do is subtract my x's. So I've got -6 minus a -2. Well, that's -6 plus 2, which is -4. And I got to square that, okay? Go back and do the same thing with your y's. 2 minus 4. Well, that's -2. And I got to square that as well. Okay? And so I've got, looks like I've got 16 plus 4, square root of 20. And of course, you may have forgotten how to reduce those without turning them into a decimal. I really wouldn't worry about decimal form. Let's keep it as precise as possible. And, you can break this apart into, we do have a perfect square, 4, perfect square factor of 4, times a non-perfect square factor, 5. 4 times 5 is 20. 4 is perfect, which means I can simplify the square root of 4 to exactly 2 times the square root of 5. Okay? So that is KL. And then GJ, I want to do the same thing with GJ, and I do see the points, they're listed there on your graph. Let's do the same thing. Let's start with the square root. Let's take our x's. 1 minus a -7. Well, that's 8. Got to square that. Plus, let's do the y's. 2 minus a -2. That's 2 plus 2, which is 4. And we got to square that. All right, so we'll end up with, that looks like 64 plus 16. Looks like we'll end up with the square root of 80. Okay, and that can be simplified. 80, you can break that down into 16 times 5. 16 times 5 is 80, and 16 is your largest perfect square factor of 80. You may not have known that, but there are other ways to get down to that. You didn't have to know right off the bat that it was 16 and 5. Some of you may have wanted to do 8 and 10. Neither are perfect, but if you keep kind of picking at it, you'll go, okay, I see that 4 times 2 is 8, 2 times 5 is 10, and you know that's perfect. That's going to give you 2. A square root times itself is the number underneath. Square root of 2 times square root of 2 is 2. You know, for example, the square root of 10 times square root of 10 is 10. Square root of 15 times square root of 15 is 15. So you get the idea, and you can't do anything with that one. So you just drop it down and then combine these two, and you got 4 times the square root of 5. So there are ways around it. You know, you're not stuck just always having to pick the, you know, the highest perfect square factor. I challenge you to try and think through that and do that, which you don't have to do it that way. You can break it down other ways, as I showed you above. All right, now we're comparing the lengths because what we're doing is up here it told us we'll prove that KL is exactly half of GJ. Is 2 times the square root of 5, is that half of 4 times the square root of 5? And the answer is yes, because half of 4 is 2. You're not going to take half of the square root of 5, you're going to take half 4. And that's 2 times the square root of 5. So yes, 2 times the square root of 5 is 1/2 of 4 times the square root of 5. So we definitely proved that numerically. We showed that the slopes are equal, thus the two segments are parallel, and we showed that KL, that mid-segment, is exactly half the length of the side opposite of it that it's parallel to. All right, so I'm going to leave the check it out for you. I advise you to do this on graph paper. I really do. I think it would be a great idea for you to lay it out, see it, see what it looks like on paper, and so you don't have to try and imagine it in your head, and then start proving that the two segments MN and RS are parallel and MN is exactly half of RS. Kind of just go through the steps and show, graph it first, and then find the coordinates of that mid-segment, the midpoints that form the mid-segment, compare the two slopes, step 2, and then finally compare the lengths. You're going to have to use the distance formula to prove that and drive that answer, okay? How about, because there's so many steps to this, let's make this a 4-pointer. I'll give a point for the graph, a point for finding the coordinates of that mid-segment, a point for comparing the slopes, and a point for finding the distances. So if you do all 4 parts, I will give you 4 points. Fair enough? All right, well, good luck, and we will talk about this in class tomorrow.